Again, we haven't covered everything yet, but it is up there. You can go through and start working on some of those problems. I would recommend you attempt the problems that look familiar that you can actually start to do. If you get held up and have some difficulties with them, you can go back to either the lecture, because maybe we did talk about it, or go into the textbook, okay, and try and find some information to help you out with it. Because ideally, you should be doing problems hopefully before we talk about it in lecture. So that way you find a problem, you have an issue, when we talk about it in lecture, hopefully it's clarified, and then that way you can go through and finish the rest of the problems. Okay? If you wait until after lecture to do all your homework and reading, it's usually going to put you behind the material. Okay? So if you can, try and start working on stuff ahead of time. This slide is going to be probably one of the most critical slides for you guys at this point. A lot of Chapter 1 is looking at Lewis structures, drawing out all sorts of things, answering questions, all kind of fun stuff along those lines. Okay? Most of that is designed to get you to internalizing all the information on this slide. Okay? So you're familiar with only looking at certain elements, different shapes. You start to get familiar with only certain particular shapes. You get familiar with how we're adjusting our drawings. So that whenever we see a point, it's a carbon. Okay? If we've got a point that is missing bonds, doesn't have enough electrons for its octet, we've got hydrogens there. Okay? So these simplifications should be immediately at the back of your mind. Okay? I would recommend actually having this out in front of you when attempting these problems. Okay? The other big thing is your common bonding patterns for carbon, nitrogen, and oxygen, the three most common elements that we're going to be dealing with this semester. So if you see a charge on an element, you need to recognize what's going to change about its bonding structure. So if carbon's positive, we would expect it to only have 3 bonds. Okay? So it's those kind of shifts and changes that ultimately we're trying to get you to discover on your own. So doing a lot of those problems will get you to kind of reinforce and build that muscle memory so that you don't have to strictly memorize these. When it comes to drawing organic molecules, the last question on quiz number 1 has you go around and try and draw as many of the possible structures for an individual formula. And hopefully what you end up finding out is that it's a pain, first off, okay? And that second off, there's a lot of structures that you can draw. Okay? The idea being that a formula is useless. So if we looked at, let's see if I can remember what it was. I think it was C4. Why is it not writing? C4H8 and 1 oxygen. Trying to put together individual Lewis structures for that. Can jump down to, let's go with a Lewis structure for this. We could go through and say we've got this compound. There's 4 oxygen. Zoom in here. And we've got now a Lewis structure, which gives us some information about our compound that the formula doesn't give us. Okay, but you'll notice that that's a bit tedious to draw out. So depending on technology, we may end up seeing different versions of this. The condensed formula is most commonly what the textbook will use, and it's usually due to typewriters. Whoops, I drew that wrong. Sorry, I just noticed that. Double bonds there. So we've got C4H, 3, 4, 5, 6, 7, 8. Yes? I think I got it right now. Okay. So what we might do is instead of drawing out the Lewis structure, which can be a bit painful, we can draw a condensed formula. And the condensed formula just attempts to show the formula, but try and include some extra information. Okay, so we could get a condensed formula. The only reason the condensed formula is still around or active is a holdover from all the old chemists. Okay? It was originally used and manipulated because of typewriters. Our technology's gotten advanced enough that we can draw out structures relatively easily, so we stop actually typing structures in and we start drawing them, okay, with better technology. We can go through and do abbreviated Lewis structures, which is similar to our condensed formula, except we would show the double bond in our condensed formula. We might add the double bond in there, so we get a little bit of extra information there. More commonly, what you'll end up moving into is a line angle abbreviated format, which is the last one I'm going to show on here. What we'll do is show all of the atoms that we can fit, okay, into a single plane. We're trying to show the bond angles appropriately within our structures. So we've got 4 carbons. There's our 4 points. We need to add on our oxygen. Whoops. So we'll add that out here. The double bond is between carbons 2 and 3. So 1, 2, and 3. There's our double bond. Okay? So it's a line angle because we're looking at just our lines. We've removed the atom information, and we're showing the bond angles as appropriately as we can as well. Okay? A full VSEPR structure is going to show the 3-dimensionality within each of these. We'll discuss why we don't need to show anything special about either of these 2 carbons in a little bit. The other carbon here, we could add some 3-dimensional characteristics to it, which is ultimately coming from our VSEPR, showing our wedges and dashes, implying the 3-dimensional characteristics of that tetrahedral carbon. Okay? If we don't have to show wedges and dashes, what do we typically do? We don't show them. Okay? It's as simple as that. Okay? So the only times you really need to use wedges and dashes will get addressed in Chapter 6. Almost every other case, unless I'm specifically asking for you to draw the 3-dimensional structure, then you don't need to show them. You can imply those hydrogens. Yes?
Tell me again what you're meaning with the arrows there.
So all I was saying is that the carbons, we'll go back to a different color so I can draw over it again. These carbons in here, we don't have to show wedges and dashes for because it doesn't make sense to show wedges and dashes for them. The only ones that, yeah, nothing is coming out of the plane of the paper. Whereas this carbon has hydrogens coming out of the plane. Technically this one does too, but I didn't draw that one. Okay? Questions about that? Okay. So a lot of what Chapter 1 is about is trying to simplify and move you into this kind of line angle abbreviated format. Okay? So everybody's favorite topic has to do with hybridization. Okay, so if we went through and took a look at the structure of, CH4. Okay, if we drew that out, we would end up with a Lewis structure, where we've got our carbon in the middle, 4 bonds out to our hydrogens. That doesn't accurately reflect the 3-dimensional structure, so what do we end up doing? We can use our dashes and wedges. For carbon being tetrahedral, we'll keep 2 lines in the plane of the paper, so they'll be kept as solid lines. Then we'll use a wedge saying it's coming out, and we'll use a dash saying it's going away. What's our bond angle? This bond angle is 109.5 degrees. Okay? We were able to figure this out. We could see it within the molecule. It was something that we could predict about our individual structures, because our electron groups need to get as far away as possible, and they all want to be in equivalent orbitals, because all of those hydrogens are the same. Okay? So our understanding of molecular bonding puts us into that framework. Okay? Well, for that bond, or for each of those lines, what are we representing by that line? Electrons. So it's where the electrons exist. Well, where did those electrons come from? From the atoms that then started to interact. Okay, and so one of the important things that we discussed at the beginning is where the electrons actually are. Okay, so what we've got to do is take our understanding of now our molecular structure and reconcile that with our understanding of atomic structure. So when we look at an atom, we've got, for carbon, our 2s, and then our 2p orbitals all available to us, and that's where our electrons were in an atomic atom of carbon. Okay? Now what we want to do is take that and say, okay, let's make a molecule out of it. Let's make CH4. Okay? We said the bond angle there had to be 109.5. Okay? 4 orbitals, 4 bonds, 4 orbitals, adds up, that makes sense. Okay, so let's just say a hydrogen comes in at 109 degrees and interacts with each of those orbitals. Okay, well, the first problem, are all of those orbitals the same? No, but in our molecular system, all of those bonds are the same. So that doesn't work. We end up with another issue. Okay, if we were going to draw our atomic orbitals on top of each other, because remember they are. Our nucleus is in the middle in each of these cases. Okay, if we were going to draw, there's our s orbital. Let's draw one of our p orbitals over the top. Okay, and one of the things we were concerned about back here was our bond angle being 109.5. Okay, well, let's go to our orbital, our atomic structure. What's the bond angle between that p orbital and that s orbital? What's the angle that separates those two orbitals? It's kind of a hard question. Are they separated? They overlap. So there isn't a bond angle of 109 between those orbitals. Okay, well, maybe the s orbital is irrelevant. That's just the tricky one. So let's throw in another p orbital. Okay, let's say, okay, well, it's just bonding to the p orbitals. What's the bond angle now between the p orbitals? $90 degrees. That's not 109.5. Okay? So our understanding of atomic theory and molecular theory don't overlap. There's something wrong with our models. So what we have to do is come up with a new way, a new model to go through and create and understand what's happening here. And that's where hybridization comes from. Okay? So that's the whole goal of hybridization, is trying to come up with some way to explain how our atomic orbitals convert and turn into molecular orbitals. Okay? And if it looks like that we're just making stuff up and it's kind of magical, that's because we are. Okay? That is literally what hybridization theory is. Someone went through, said it didn't work. Let's just mash stuff up until it works. Okay? So let's take it a little bit further. In the example we were just looking at, so we're looking at CH4, okay, methane. Sorry, this is going to be drawn kind of ugly. Okay, we need 4 equivalent bonds, 4 equivalent areas where we can put electrons for our ultimate shape. Okay, the bond angle between those needs to be 109.5. Okay, so what someone came through and said is, I need 4 new orbitals. So one thing we can kind of ignore here is where I've got sp3 written. Let's cross that out for the moment. We need 4 a orbitals, new orbital. Okay, so I'm going to go back to my atomic orbitals. Okay, and based on some laws of physics, I'm going to run under some particular assumptions. Number 1, I can't create or destroy matter. An orbital, we're going to treat as matter. So if I start with an orbital, I need to end with that orbital. Okay, I can change how it looks, but I have to have the same number. So if I start with 4 orbitals, I need to end with 4 orbitals. Okay? So what somebody went through and did is said, okay, well, if I have to have 4, that means I'm going to have to take all 4, mash them all together, treat them like Play-Doh, and make 4 new 100% equivalent orbitals. And that's what they did. Okay? Now each of these orbitals, and this is in theory drawn in 3 dimensions, which of course you can't see. Okay? Each of these orbitals are now 109.5 degrees away from each other, and we have generated our molecular orbitals. Okay? Our bonding orbitals that represent accurately the bonding structure for CH4. Okay? We just made it up. That's all it was. Okay? So we need to come up with a name for that. Okay, this is where I temporarily said, okay, we just made these new orbitals. We'll call them A orbitals. Okay, chemists aren't the most creative, so they wanted to come up with a name that represented where these orbitals came from. Okay, well, what orbitals did I use to make these new orbitals? I used s orbitals and I used p orbitals. How many s orbitals did I use? 1. So what do we use for the name? You end up seeing just the s. What's the superscript? How many of these are there? Technically, there's a 1 there. I then took some p orbitals, so I can now add that in here too. There's my p orbitals. How many p orbitals did I use? I had to use all 3. Okay, a student showed me this. I didn't like it at first, but now everybody seems to like it, so I have to keep showing it because everybody likes it. Okay, we needed 4 new orbitals for this. 1 plus 3 is, there's your 4 orbitals. So if you have 4 groups of electrons, your hybridization needs to be sp3 because s1, p3 gives us our 4. Okay, it's a tenuous relationship, but hey, it works. Okay, does that kind of make sense? What happens if I don't need 4 equivalent orbitals? Say we change our structure now. I'm going to regret doing this because right after I draw it, it's going to erase it. I take a look at, say, this compound. And I want to look at the molecular orbitals for that carbon. Okay. Well, we could go through, we're looking at the same idea, how many groups of electrons are around this individual structure. Okay, well, we don't have any non-bonding electrons to worry about, but we've got electrons in this bond that are unique. We've got electrons in this bond, also unique to a different atom. I have 2 lines here, which is how I get my octet for a carbon, but are those electrons in a unique situation? Not really. They're both attached to the same atom. Okay? So even though I have 2 bonds here, I'm going to treat that as 1 group of electrons. Okay? So I've got 3 groups of electrons around this carbon, which means as far as my bonding, my molecular shape goes, I need 3 orbitals to explain those electron groups. Okay, so if I'm now going to go through and try and build my hybridization, again, I need 3, but I start with 4. Remember, I can't create or destroy orbitals, which is why when we started, if I needed 4, I had to use all 4. But now I only need 3. What 3 do I use? Okay, we'll use the S. I need 2 more. And I'll use 2 p's, and I end up with sp2. Why don't I just hybridize just the p orbitals? Why do I always start with the s? The energy level. Your s orbital is lower in energy than your p orbitals. We're always striving for the lowest energy possible. When we're going to go through and hybridize, we always hybridize the s orbital because it's the lowest in energy. Okay, that's why you always have to start with it. So what ends up happening as far as our structure goes? Well, when we make our sp2, we generate our 3 hybrid orbitals. We'll call those our sp2 orbitals. But that's only 3. I started with 4. What happened to my 4th orbital? Did I use it? No. Did I get rid of it? No, it's still there. So what happens? I have a p orbital left over. This p orbital can now do some other fun stuff. Okay, and that's going to be where our double bond comes into play. Okay? What happens if I have only 2 groups of electrons around an atom? Now I'm going to shift to an sp. Okay? So now I'm going to take just an s and 1 p orbital. I'm going to make my 2 new sp orbitals, but I didn't use what? 2 p orbitals. So those are now left over. Okay? There's some other information involved in here. You'll notice that the energy axis shows up on each of these. Okay? The energy of our s orbital is at that flat line, and I'm showing the p orbital somewhere above it. Where should the energy of our hybrid orbitals be? Should it be at the same level as our s orbital? Below our s orbital? Higher than our p orbital? Okay. We're taking an average of our s and p orbitals. So if we take the average, where should our energy be? Somewhere in between for each of these. Okay? So if you look, in theory I did this right, each of those hybrid orbitals is greater than our 0 energy for our s orbital, but still less than the energy for our p orbitals. Okay, so those heights are very carefully irritating. Okay, so if we draw a line across for our p orbitals, you'll notice they're always above our sp hybrids. Okay? Which of these orbitals would you predict to be the most reactive? sp3, sp2, or sp? sp3, why? What's that? It's got more what in it?
More electron pull.
No, there's no difference in our electronegativity. What were you suggesting? One what left? When we go through an average, okay, if I average these two, where am I going to be as far as my energy? Exactly in between them, right? If I average 3 values now, though, what happens to my average? It's going to float a little bit higher, closer, because I'm now weighting the higher energy. So if we were going to try and predict something about the reactivity of these 3 types, we might predict the sp3 to be more reactive than the sp, or sp2 and the sp, because there's more p energy or p orbital in it. The p orbital is higher in energy, which is going to make our hybrid orbital also higher in energy. Yes?
But if you haven't matched the p, wouldn't that be more likely to
So
go off into?
that's why I didn't rank the p orbital in that. If we're going to compare our hybrid orbitals, sp3 should be higher in energy than our sp2, higher in energy than our sp. Our p orbital will be higher in energy than all of them. Yes. Okay? Questions about that?
So which one was the higher? The sp, you're saying?
The sp has the lowest energy. Your p orbital will be the highest energy, followed by your sp3, followed by your sp2, followed by your sp. Okay? Other questions with that? I'm pretty sure.
When would we see?
We'll look at some examples where the p shows up. Okay? So all we've looked at now is those basic structures, and we haven't evaluated what we can do with those p orbitals or what we can do with those sp orbitals. So what we're going to go through and do, let me actually just skip one more further ahead. Yeah. We're going to take a look at a couple examples. Those examples are shown up at the top here. So we've got NH3 and CO2. So let's take a look at NH3. So we draw out our Lewis structure first. To start off our Lewis structure for NH3, what do we need to do? Starting off all Lewis structures, what do you need to figure out? No. 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 Valence electrons, that's what I want to hear. Total valence electrons. How many electrons does nitrogen come in with? 5. Hydrogen comes in with 1. There's 3 of them. We need 8 total electrons in our structure. We can now pick our central atom. Our central atom in this case will be nitrogen. We can draw on the rest of our, I'm skipping steps here. Go through and we end up with NH3 here as our structure. Can anybody have problems seeing that? In green? Okay, then we'll leave it. How many groups of electrons are around that nitrogen? Okay, before we looked at bonds. So we could look and just say there's 3 bonds. And you'd be right, there are 3 bonds, and each of those bonds is a group of electrons. But that lone pair is also a group of electrons. Okay? So we have 4 groups of electrons around here, which means I need to come up with 4 equivalent orbitals, molecular orbitals, for this. So how would I do that? What do I end up with? I end up with my sp3. I think I was initially going to draw this out. Glad I changed my mind. We'd end up with 4 sp3 orbitals. Okay? What shape would we get from that? Tetrahedral. What bond angle? Good, that's all I wanted to hear on that. 109.5. Okay. Your textbook will mention that this is not exactly 109.5. Why is it not? Because that lone electron pair is not officially exactly the same as our bonds to hydrogen, which changes the structure slightly. Okay, just be aware of that. Your textbook will talk about it. As far as I'm concerned, 109.5 is perfectly valid. Okay? So what happens when we move, let me step back away from that. So that's our nitrogen. What about our hydrogen? How many groups of electrons are around our hydrogen? It's only one group. Do we need to hybridize? No. So what's the molecular orbital that hydrogen's using? Just an s orbital. So if I want to go through now and say what is the... Oh, I've used red already. I got too color happy on this slide. If I take a look at that bond now between the nitrogen and the hydrogen, and I ask what orbitals are involved in that bond, what would you tell me? What orbitals made that bond? What atoms are contributing to that bond? Nitrogen and hydrogen. What are the orbitals on nitrogen? sp3. What are the orbitals on hydrogen? S. What orbitals made the bond that connects those? An sp3 and an s orbital. We can add some extra information. It's not just an sp3 orbital, it's an sp3 orbital from nitrogen. It's not just an s orbital, it's an s orbital from hydrogen. Okay? So we can now start to classify what orbitals went into making individual bonds. Okay? You will see problems like that. Okay? Does that kind of make sense?
Would you write it the way you have it there, or you would just say it's sp4?
So I know what you're trying to do there, but I don't think you said it right. You want to try that again?
sp4, right?
No.
Go to D, right?
Yeah. So maybe what you were trying to attempt to do is condense that all together and say it was 2 s orbitals and 3 p orbitals? Is that what you were thinking? No, don't do that.
What is the 4 times the sp3 of the nitrogen?
There are 4 sp3 orbitals. So remember, sp3 is the name of the orbital. Okay? To make an sp3 orbital, I needed 1 s and 3 p's. Okay? So if I'm going to make those orbitals, so here, we'll go through and draw them. We're going to draw them out. If I'm going to draw the sp3 orbitals for our nitrogen, we've got 1, 2, 3, and then this one. That was terribly drawn, but you get the idea. Okay. There are my 4 hybrid orbitals. What is that orbital name? What do I call that orbital? What's the name of one of those? It's sp3. How many sp3 orbitals do I have?
That's where I don't know how you're getting the 4.
Okay. That 4 comes from, in the process of making these orbitals, I can't create or destroy my atomic orbitals. I can change my atomic orbitals. So when I go through, I'm going to take all 4 of these orbitals, mash them all into one giant pile, and I'm going to pull out new orbitals. These new orbitals I give the boneheaded name of sp3. I started with 4 orbitals. I must end with 4 orbitals. So if I take 4 and put them in, I'm going to make 4 coming out. They're just going to be different shapes. Yes, no?
No, but it's okay.
Okay, we can talk about it more after class. Other questions on that? Yes?
Why wouldn't you call that a bed trigonal or whatever? And why contact?
Going through a different name for it. Officially, it is not tetrahedral. What shape is it? You started to get it. Trigonal. Right idea, trigonal pyramidal.
Oh, okay.
That's not how you spell pyramidal. That looks better. Ish. Okay. Yes, officially that is the name. The reason why I'm not pushing that aspect of it is it's not important. If you start saying it's trigonal pyramidal, then what's the bond angle?
More than 1.5.
It goes the other way. It goes less. Okay. That means you have more stuff to memorize, where it doesn't add any useful information. Okay. So you will see that referenced. But as far as the electron geometry goes, it's tetrahedral. As far as the bond geometry goes, it's trigonal pyramidal. That difference isn't enough to make it worth talking about more than we just did. Does that make sense? Yes?
When we write this, do we know the big 4 SP3s, or does the fact that it's SP3 note?
If it's SP3, there has to be 4. If it's SP2, there has to be 3. If it's SP, has to be 2. Other questions? Okay, let's take a step back from all this SP stuff and try and ask a really easy question that's probably going to be so easy you're not going to be able to answer it. But we'll try it anyway. Maybe you'll get it. We'll see. That bond. What kind of bond is that? Hydrogen, no. Covalent, that's a different class. Right idea on where we're trying to transition. It's not covalent, though. It's a polar covalent bond. But again, not the answer I wanted. Keep going. How else can you tell me about that bond? Maybe I heard it. Single. It's a single bond. There's only one bond there. Okay, like I said, I was going for a really easy answer. Okay, why do I want to go with that? Well, if we've got a single bond, being chemists, single bonds, that's way too easy. We don't want to refer to it as a single bond, so we're going to start to imply some more information about it, and we're going to call it something else. We can refer to it as a sigma bond. Okay, sigma is a little bit more versatile than single, double, or triple. Okay, and we'll talk about that with the next example. Another thing that you can remember here, S, single. Okay, they both begin with S. That works out. What else is nice about it? What orbitals are involved in a sigma bond? We're always dealing with some type of S orbital, be it an sp3 hybridized one with an S orbital, or an sp2 with an S orbital, or an sp2 with another S orbital. When we're looking at our sigma bonds, we're always looking at some, whoops, went the wrong direction on that. We're always looking at some S type of orbital. Okay? And that's shown actually typed on the next slide, which we'll get to in a second. Okay? So, let's push on a little bit further and move into CO2. I didn't want to do that. I just wanted to erase. So let's take a look at CO2. I'm going to assume that you can go through and draw it on your own or figure it out on your own, so I'm just going to draw it up here. You did all that fantastic work. Good job. You got the right answer. There's CO2. What's the hybridization of the carbon? How many groups of electrons are around this? We only have 2. We have 4 total bonds, but our double bonds are occupying the same space. We'll count them as one group. So 2 groups means sp hybridization. How many orbitals would we get out of that? We end up with 2 orbitals, 2 sp orbitals for our carbon. What about our oxygen? Where are electron groups? There's 1, 2, 3. 3 groups of electrons. sp2. I'm going to stop drawing those because I don't think that's really adding anything. And we get 3 sp2 hybrid orbitals. Okay, so if I asked you, and this is where the question is going to get kind of tricky, what orbitals made that bond, our now blue bond? From our carbon, we had an sp orbital. From our oxygen, we had an sp2. Well, that was pretty straightforward. What orbitals made the entire bond that's now circled? How many bonds are now circled? 2. We've got a single and a double. Okay? That double bond gets a little bit trickier to classify. When we go through and build our structures for these, what we're going to end up finding, I should have picked a better drawing because I'm not going to draw it. Our carbon is sp hybridized. So if we picked our carbon, we'd have our bond out. Our oxygen would have a bond in, and we'd have 120 degrees around our oxygen because it's sp2 hybridized. So there would be our lone pairs out there. That overlap accounts for how many bonds? How many bonds did it account for? 1 bond. Where do I get the second bond from? Okay. Well, maybe it's the other sp orbital. What's the other sp orbital doing, though? Bonding to the other oxygen. Okay, so something's missing here. We can't account for that double bond based on what we've got drawn. Did I draw all the orbitals? No. What did I leave off? In the case of the carbon, I have 2 p orbitals left over. In the case of the oxygen, I have 1 p orbital left over. Okay? Those leftover p orbitals, as long as they are parallel to each other, can form our second bond. Okay? And this is where it gets terribly difficult to draw. Your textbook has some nice pictures, but what I'm going to try and do is take this structure here. Okay? Everything's in the plane right now, so what I'm going to do is take this and rotate it up and out. Okay? So if we look at the carbon single bonded to the oxygen, it's still in the plane of the paper. Okay? So we're just taking this and just rotating it. Okay? Our lone pairs now, though, where would those be located? One's kind of coming at you, the other one going away. Okay, so we can draw those on now here. Just so you know, this is really bad form to draw wedges and dashes for your lone pairs. Okay, we're doing this so that we can help find where that p orbital is, so we can see it a little bit better. Okay, this p orbital, okay, just like when we went through and built our sp2 orbitals, we aligned them so they can all get as far away from each other as possible, because we want those electrons as far away as possible. What is this p orbital going to do then? Get as far away as possible from those 3. Well, those 3 oriented just like this, okay, all on the plane. Where's as far away as this p orbital can get? Could it be right here in this plane? We'd have the lobe of our p orbital, one coming over this direction, one going over that direction. Is that p orbital lobe really far away from one of our sp? No, it's right in the plane. Whoop, that's not very good. Okay, so we could say, okay, maybe it goes here. That's better but then it's still pretty close to our lone pairs. Where can it get as far away as possible? Coming in and out of the board at us. That's god-awful to see. Okay? So how could we change our perspective on that? Well, that's why we drew this. So as we take our structure, I'm going to set this down. Actually, I can use this. Here's the plane of our molecule. And we've got our p orbital coming in and out of the plane. What did I say? We're going to take it and rotate it. Where's our p orbital now? Up and down in the plane of our paper. So we can now draw it on there so we can see it. Okay. Our carbon has one of those too. Single bonds are fun, or sigma bonds are fun, because they can freely rotate. Okay? As I rotate that bond, that orbital overlap never changes. It's always directly overlapping. What happens with my p orbitals, though? Okay, so if we take two pens, treat those as our p orbitals. Okay? Let's say they were like this. What happens is I rotate the bond. Do our p orbitals overlap anymore? No. Well, to form a bond, what do we need? We need overlap. So what happens when we move up to a double bond or multiple bonds? Our molecule starts to get fixed, and it stops being able to rotate because we lose that p orbital overlap. Okay? So we get what I would refer to as an indirect overlap. And our structure will align itself such that those p orbitals interact with each other. And you're always going to see it drawn where it overlaps top and bottom. What does that start to look like? There's one bond, there's another bond. Starts to look like three bonds. It's not. Okay. We've got our sigma bond through the middle, which is the overlap of our hybrid orbitals. Then we've got our double bond, which is the overlap of our p orbitals. Our p orbitals will overlap both above and below our molecule. Okay? But that still counts as only one orbital interaction. Okay? So what we've now done is come up with a way to explain how we can get multiple bonds. Okay? Remember, electrons like to repel each other. How could we possibly get 4 electrons into the same space? We don't. We put 2 electrons into a sigma bond that runs between them, and then we put 2 more electrons into the p orbitals on the outside. Those p orbitals can now interact with each other in such a way that we can get a second bond just outside of the space of our sigma bond. Does it kind of make sense? Okay, so let's come up with some other names with this. What orbitals did we use to make this? P orbitals. Okay, so we could say the orbitals used were, just because I like repeating myself, p orbitals. P orbitals, that's nice. We could refer to it based on that. How else could we refer to it? We can now start to shift back to our Greek letters. For our sigma bonds, our single bonds, we had sigma for single. Here we're going to use pi for double and triple. So instead of doing double and triple, let's call it capital P pole. Okay? So we get P's running through the name. Anytime you have a multiple bond, double or triple, that's composed of a pi bond. What orbitals make your pi bond? Your p orbitals. And, because your pi bond only makes one bond, where's the second bond come from? The sigma bond that runs through the middle. So if we go through and circle all the way back to that initial question, okay, and I want to know what orbitals are involved in making all the bonds that are now in that blue arrow. We get a carbon sp, sigma bond, carbon sp to an oxygen sp2, and we get a pi bond. What orbital is involved in the pi bond? A carbon p orbital bound to an oxygen p orbital. Okay, I know there's a lot of drawing on there. But as soon as I try and erase something, it erases everything. So, yes.
Is that a dot in between the pi and sigma? Or the pi dot? Oh, thank you.
That's what I was guessing you were asking. Yeah, it's a colon. Okay. Hybridization theory takes a little bit of practice to get used to. Ultimately, what we're going to do is refer back to it every so often. You might hear me say, what orbital are these electrons in? Okay. You need to be able to quickly refer back and say, oh yeah, that's going to be, that carbon was sp2. We're looking at the lone pair on that carbon. Well, that's going to be sp3 or sp2 orbitals, depending on what structure is going on. Okay? Because that then gives you something about the reactivity. How do you know it gives you something about the reactivity? Which do we say was more reactive? Our sp3, or even more reactive, our p orbitals. So if we have an idea of where our electrons are located as far as their orbital energies, we can start to predict something about how reactive they're going to be reacting with something else in, say, a reaction. That was 3 times. I thought it was funny. Okay. Questions about that? Yes?
So I might be getting ahead of myself, but going to the next level, like on the quiz, where you don't have the Lewis structure.
So where you don't have the Lewis structure, your first step is going to be
Make a Lewis structure.
make the Lewis structure.
Okay.
Yep. So on the quiz, what question is that?
4.
4? Yeah, question 4. You're going to have to go back to those simplifications. Now it's going to erase everything, so I hope you didn't want any of that. All the way back to that guy and start to apply those definitions. Okay? The one extra thing that I'll add is your aluminum. Remember I said it's special. It's happy with just 6 electrons around it, or 3 bonds. Okay? What hybridization would you expect of an aluminum atom then? sp2. 3 electron groups, 3 bonds. Okay? Okay. So this was kind of the summary. We just talked about all of that. Okay? So I guess I can't really go into it, or I won't go into it again. We just looked at our nitrogen, our ammonia, and we said our sigma bonds. Okay, they were connected by our sigma bonds. That's where we had our p orbitals, or our sp orbitals. We might use the p orbitals in that, but we don't have to. We do have to use the s orbitals to form our sigma bonds. Okay? Our p orbitals will be involved in multiple bonds, so double or triple bonds. That's where we can refer to them as pi bonds. You'll see the symbol pi, and that's where we get that indirect overlap. Okay, so if we're going to draw that again, we'll probably come back to this some more. If we looked at an sp3 and another sp3, if we were going to show those actually forming a bond, we would probably draw it a little bit better where they directly overlapped in the middle, like a nice little pie chart there. Okay, if we looked at a p orbital, okay, we'll never get those to directly overlap. Why would they never directly overlap? Is it ever just p orbitals interacting? No, it's 2 atoms. There's our p orbitals, and there's our sp orbitals. Why do we never see the p orbitals overlap? Because our sp orbitals start to get close enough to each other that they start to repel. So our p orbitals never directly overlap. Okay? This is one of the fun things with chemistry and quantum chemistry. That gap in between is where technically the electrons cannot exist. But what's fun is we get 2 groups of electrons close enough to each other, they can jump through nothing. Okay? Which sounds really weird, but that's what's actually happening. We've got them close enough that the electron sees that space and says, you know what? I don't care if I can't exist in between here. I'm just going to be over here. Whoop, now I'm over there. Now I'm over there. Okay? Because we've got them close enough to each other. Okay? Questions about our sigma versus pi and hybridization and all that fun stuff? Okay. So we can take a deep breath. Step away a little bit. I know this has a lot of things on it, but this is trying to simplify things again. Okay, this is kind of a summary of VSEPR models and hybridizations. Some people are better at shapes. So if you draw out an individual structure, maybe you can recognize that it's trigonal planar right away. Well, if it's trigonal planar, what's your hybridization? sp2. Okay? If it's tetrahedral, it will be sp3. Okay? So you can try and get some of that hybridization information through looking at the actual spatial geometries, or those shapes. Okay? Because you'd asked about it or mentioned it before, we do get those other shapes over here. They'll show up in the slides. I might mention them in passing in class. I don't think I'll ever test you directly on those shapes. Okay? So some other things to be concerned about, which we've got on the left. When we were completing an octet, we want to count the electrons around our atom. Okay? So the electrons that we can count for that would be our lone pairs, our sigma bonds, and our pi bonds. Okay? We can count all of those electrons to make sure we've satisfied our Lewis rules of an octet. Okay? When we move into hybridization, we stop looking at all the electrons around it, and we only focus on our groups. Our groups are going to be defined as our lone pairs and our sigma bonds. So when we went back to CO2, or if we go back to CO2, and we drew that out where I don't really have any space, let's say upper right-hand corner. And I didn't tell you this rule to begin with, but now we want to count the electron groups around CO2, or around our carbon. Well, what groups can we count? We can only count lone pairs and sigma bonds. How many groups are around carbon? 2. We don't worry about the pi bonds. We're only concerned about the single bond. In there, anything greater than a single bond, we ignore that extra bond. Okay? Make sense? Ish? Okay. This is kind of, sort of starting chapter 2 in a very vague way. This is more kind of covering some information that I think is should have some more importance, but I didn't find it in your textbook directly. So let's kind of now step away from all of this hybridization theory and kind of get into what we're ultimately going to have to do is start applying it. Okay? So we want to look at the roots of functionality, or how molecules react. Okay? So everything is ultimately striving for neutrality, our zero energy level. Okay? So what might be something, or might be one way that we can get something off of that zero energy level, okay, or not neutral? Say if I drew something like that, NaCl, and heck, I'll be nice, I'll even draw on the lone pairs. When you think of the chemistry of sodium chloride, is that what you think of, that structure? Anybody think of something different that might rhyme with scion? How about ions? What rhymes with ion? Typically, when we think about the reactivity of sodium chloride, we don't look at the Lewis structure. We look at those ions. How did we get to those ions? Why is chloride negative and the sodium positive? It's electronegativity. Okay? A huge answer for why. If I ever ask you why, electronegativity, it can be a gut reflex. Okay? Probably 50% of the time you'll be right. Okay? So you need to be familiar with a lot of the electronegativities of these elements. Okay? Remember, we simplified the periodic table down to roughly 10 elements. Okay? So you might start looking at those, getting kind of familiar with what their electronegativities are, so you can start to apply those definitions a little bit. Okay? We took it a step further, and we simplified that way long ago when we looked at the types of intermolecular bonds, or intramolecular bonds. We looked at ionic, polar covalent, and covalent. Okay? And those generated different functionalities. When we looked at the ionic bond, we said a metal and a nonmetal was our tip-off, or ions. So we could look over at our structure and we could say we've got an ionic bond. How do we know it's ionic? Well, it has the charges or the ions. Why did we get those charges? Because the difference in electronegativity. What's that difference? Oxygen, second most electronegative element on the periodic table. Sodium, really, really low. So we see a huge difference in electronegativity. So huge we see the ions form. We now know something about the reactivity of these molecules, or this molecule, because I have a negative charge. What do I want to stabilize a negative charge? Positive charge. So if I put this compound in a solution that has a really good positive charge, the positive charge might react with a negative charge, and now I've got a product of my reaction. Okay? Well, what happens when we move outside of ionic materials? Because most of the chemistry we're going to do is not going to be ionic. Probably going to be polar covalent or covalent. We need to come up with some way that we can translate that information. Well, covalent. Would we predict covalent bonds to be reactive? So let's pick an example of the easy one. Anything bound to itself. Carbon bound to carbon. What partial charge is on carbon? Sorry, the first carbon. How about this draw? Let's try that. Maybe that'll help. If I take a carbon and I bond it to carbon, what partial charge is on each of those carbons? How do we get that partial charge? How did we get the full charge up here? Oxygen was wickedly electronegative, taking all the electrons away from sodium. Let's do that same rule down here. Which carbon is more electronegative than the other carbon? Neither. So what partial charge builds on those carbons? 0. Nothing. If it's neutral, does it want to react? No. So when we're looking at organic chemistry, if we see covalent bonds, or strict nonpolar covalent, carbons bound to carbons, or carbons bound to hydrogens, we would predict those bonds to not be reactive, because we don't generate those charges. How about polar covalent? So polar covalent is somewhere in between these two. And we came up with a rule, anything bound to oxygen, nitrogen, or a halogen. What's special about oxygen, nitrogen, or the halogens? Come on. If we take a look at our electronegativities, they're all relatively really high. There's another feature that comes into play which we'll talk about later. Okay? But our electronegativities for our halogens are all relatively very high. What does that mean about a bond, say between carbon and any one of those? It's really reactive because we start to form those charges. They're not full charges, so how would we represent it? We said carbon to oxygen. Which one would be more negative? Which one's more positive? But it's not fully positive and negative. How can I show that it's not fully positive and negative? And show my little lowercase delta. The other thing you might see would be the dipole arrow, showing the flow of electrons moving from the carbon, which is positively charged, towards our oxygen. Okay? So now if I take this bond and throw it into a solution, if I've got something in solution that's relatively positive, which atom here is likely to react? The oxygen. If I throw it into a solution that has a really big negative, which atom's likely to react? The carbon. Okay? So being able to track and relate the bond characteristics back to electronegativity can start to push answers for you without having to know much else about how it's actually occurring. Okay? So it can be very, very helpful to be familiar with that. So if we look at functionality and structure, so let's pick HCl. If we were going to draw out HCl, what would it look like? Good answer. Hydrogen, chlorine, lone pairs around our chlorine. Okay, let's pretend we don't know anything about reactivity of HCl. Do we have a polar bond? Do we have a polar covalent bond? Let me rephrase that. Do we have something bound to oxygen, nitrogen, or a halogen? Yes. Chlorine's one of the halogens. So what starts to build on our structure? If we have a polar covalent bond, what happens to the hydrogen? It becomes more positive. Why positive? Lower electronegativity than the chlorine. What happens to the chlorine? Becomes more negative. So we can start to predict something about the reactivity of this molecule. We have a relatively positive hydrogen and a relatively negative chlorine. Hydrochloric acid does what in water? What's the definition? We'll come back to it. It's all chapter 2. It's a Bronsted acid. It donates hydrogen ion. You just predicted the reactivity by knowing something about the difference in electronegativity. Okay, let's pretend that you don't see the name up here. Okay, actually I'm going to say the name down here. Let's pretend you don't see the name down there. I lied. I didn't want you to see the name up there, but I figured I'd distract you. Okay, so if we go through and draw out the structure for this compound, okay, it might take a little bit of practice getting used to drawing out our Lewis structures. Might take a little bit more practice because there should be 2 carbons there. And we get our Lewis structure. We want to come up with some idea for the reactivity of this molecule. So what we're looking at over here is finding positives and negatives. So what part of this molecule might be completely irrelevant for us to be concerned about? The hydrogens with the carbon. Why? The electronegativities are virtually the same, which means what type of bond? Covalent. So we can ignore that part of the structure. That's nice. What can you tell me about the rest of this structure? The carbon is probably positive. Why? 2 oxygens on the side. What can you tell me about the rest of the atoms? If the carbon's positive, the oxygens are going to have to be negative. What about that hydrogen? Why should it be positive? Because it's attached to that oxygen. Okay? Which positive is going to be more positive? Okay, we might predict the carbon. Why do you predict the carbon? 2 oxygens attached to it. Reasonable thought process. One of the things that we will see when we move into the acid-base chemistry is that there's other things that affect it. It's not just how many oxygens attached to it, but then also the stability of the product. Okay? That carbon, while it may be positive, if we try to bring something in to react with it, we'd have to form a 4th bond. We'd have a lot of very electronegative things around it. That's not very stable. So carbon, while it might be partially positive here, isn't actually all that bad. Okay? And like I said, we'll come back and address that towards the end of the semester, actually. But let's compare carbon to hydrogen. What's the difference between carbon and hydrogen? They're roughly the same electronegativity, but are they the same? No, they're not the same. Okay? Hydrogen is lower in electronegativity. So if we look just based at a single oxygen attached to it, this hydrogen should be more positive than that carbon. What does that mean about the potential reactivity of that hydrogen? Should be fairly reactive as a positive. Have we seen hydrogen being positive before, reacting in other cases? What did this molecule act as? An acid. What do you think this molecule might act as? An acid. What was the name again? Acetic acid. Okay? So we can start to predict something about the chemistry of these molecules by looking at those differences in electronegativity. Okay? I'll let you work through some of those other ones on your own. I kind of want to push a little bit further and see what else we've got here.
Was the answer to your question of which is more positive, was that hydrogen then?
Yes.
Okay.
So other things that we can see coming out of chemistry. Okay? There's other observables that we might classify as not chemistry, or most people don't classify as chemistry. Okay? Solid sodium hydroxide. Okay? The observable being that sodium hydroxide is a solid. How about liquid water? There's another observable. How about gaseous CH4 or gaseous CO2? Why are each of those compounds in those physical states? That's chemistry. What's keeping them in those physical states? Let's take a look at CH4 versus water. If we drew out those structures. Okay? For a Lewis structure for water, we would draw it bent. Why do we show it bent? Because it's tetrahedral in nature, but because we got those two lone pairs, we end up showing it in that bent shape. And we've got CH4, which is straight up tetrahedral. Okay. Roughly the same molecular weight, but one is in liquid phase, the other one's gaseous. So one has virtually zero interaction with other molecules, the other one is interacting fairly frequently, okay, fairly close contact with other molecules. Why? They've got the same weight. It comes back to the polarity of each of those molecules. Okay? If we look at CH4, what types of bonds do we have in that? All covalent, which means what's the partial charge on the hydrogen? None. What's the partial charge on the carbon? None. So if we look at this molecule's need to react with another one, there's no charges to react. Okay? Neutral, nothing. That's not how you spell neutral either, is it? Close enough. Okay? It's neutral, so it doesn't really have any reason to interact with something else. What happens with water? We do have the lone pairs, but I don't want you looking at lone pairs. I want you looking at the bonds. We have a bond between oxygen and hydrogen. What type of bond is that? Polar covalent. What charge builds on the hydrogen? Partially positive. What charge builds on the oxygen? Partially negative. Okay? CH4, or methane, was neutral. No reason to interact with anything else. Water has some partial charges. Okay? Everything is striving for neutrality. How can I neutralize that positive hydrogen? I need to bring in a negative. If I'm in a solution, where do I have a negative? From another molecule of oxygen. And I start to build an interaction between those two atoms. That's not a bond, by the way. That interaction I don't get in methane. Okay? So now if I'm going to look at the phases, all the phases is the energy required to rip two molecules apart. Methane doesn't want to interact with anything anyway. So how much energy is it going to take to rip it apart? Virtually nothing, which is why it's already in its gaseous state. What happens when we move to liquid water? There's a lot of energy trying to neutralize those charges, which means we're going to see a phase change. It's actually going to hold on to other molecules. Okay? And what we're starting to look at and what we'll move into, which I believe is what our next slide is our intermolecular forces. Okay? And no, I'm not going to draw this all out right now. Okay? So we'll go ahead and end it there.